The story so far is that Newton took his first law from Galileo, who said that if you don't apply a force to something, it doesn't change its velocity. And then he developed his second law, which makes the first law really just a special case of his second law, which tells you exactly how things accelerate when you apply forces to them. So the mass times acceleration is equal to the sum of the forces acting on something. So if you want to know how something moves, all you need to know is all the forces. And Newton's second law is correct provided you don't go too fast, so that relativity becomes important, or you don't look at things that are too small, so that quantum mechanics becomes important. So it's a very, very powerful tool for calculating things. But you do need to know all the forces that apply to things. And one of the ways to help that is to look at Newton's third law, which tells us an important rule that forces have to obey. Fundamentally, all forces come from interactions. So a force arises where you have something, here I have something A, and something else, B, and they have some kind of interaction. Now we only know of a few fundamental kinds of interactions. We know about gravity, we know about electromagnetism, we know about the nuclear strong force and the nuclear weak force. But all forces, no matter where they come from, all follow Newton's third law. And Newton's third law says that all forces come in pairs. So the force on particle A due to particle B has to be paired with an equal and opposite force on particle B due to particle A. So in other words, you've got one force going one way, one force going the other way. They're exactly the same magnitude, so if you add them up, you'll get zero. And that's Newton's third law. So you can get examples anytime you have any kind of force. And indeed, every time you have a force, you can do an example of Newton's third law. Let's start with if you're lifting a book. So if you lift a book, there's a force by you to push up the book, and there's a force by the book pushing down on your hand. It's a hand-book interaction. Or you might have a plane. If you have a plane's propeller, there you have the plane pushing on the air, the propeller pushes the air, and also the air pushes the plane. That's how the plane goes forward. It's a propeller-air interaction. You might have a swimmer in water. The reason the swimmer pushes on the water is in order for the reaction, the water pushing on the person, to push them forward. It's a person-water interaction. Or you might have a cricketer. And if a cricketer hits a cricket ball, then the ball experiences a big force, but the bat experiences an equal and opposite force. And that's why she has to hold it very firmly and also hit the ball right in the middle so that it doesn't twist in her hands, due to the bat-ball interaction. So in each of these cases, all you have to do is figure out what two things are interacting, and that tells you how to apply Newton's third law. And the force between the two things is going to be equal and opposite. Now there are some very common misconceptions that people fall into when they look at Newton's third law. And the first is when a big thing interacts with a small thing, that the big thing applies a bigger force. For example, if you step on a blade of grass, then yes, there's a very large force on that blade of grass from your body weight, but in fact, there's an equal and opposite force from that blade of grass up on you. But even though that force is equal, the same force will do a lot more to a blade of grass than it will do to a foot. And so the real way this works is that big things respond to forces less sensitively than small things. The next misconception is that a force is something that an object can have. For example, a big magnet, people might say, has a big magnetic force. Or the Earth, they might say, has a large gravitational force. But the reality is that all forces come in pairs, and they're the interaction between two objects. So a big magnet doesn't have a big force. A big magnet and something else can exert an equal and opposite force on each other, which may or may not be big. And similarly, the Earth doesn't have a large gravitational force. The Earth and some other mass together can exert a mutual equal and opposite gravitational force on each other. The third misconception is that balanced forces on an object exist because of Newton's third law. So for example, if I'm standing on the Earth, then there's a force of gravity on me, pulling me down, and there's a force due to the ground, pushing me up. It's often called the normal force. And the fact that I'm neither accelerating up into the sky nor down through the Earth means that the normal force is exactly equal and opposite to the gravitational force. And that's why I stand still. But those are not the Newton's third law equal and opposite forces, because they're both acting on me. In fact, they come from two different interactions. The interaction from the gravity is because of the existence of the Earth and its enormous mass and me. It's a gravitational attraction between me and the Earth. So the equal and opposite force from Newton's third law for that is my pull on the Earth. So I'm pulling the Earth up gravitationally, just as the Earth is pulling me down. And the interaction for the normal force is the existence of the ground. If I was instead standing on water, then I would find that the gravity would indeed accelerate me downwards. And so the Newton's third law pair for that is my force on the ground. If I was standing on thin ice, then that force would break the ice. And so the normal force is about the interaction between me and the actual surface I'm standing on, and the gravitational force is between my mass and the Earth's mass. So because Newton's law describes forces on two objects, and there's only ever one of those forces on each object, they can never balance. So they never balance on an object. If they could, then what Newton's third law would be saying is that there's always an equal and opposite force on that same object, and so there'd be no such thing as force. They'd always cancel. But they don't always cancel. If I'm pushing on someone, someone's pushing on me, we both get pushed. We get pushed in equal and opposite directions, but there's definitely pushing happen on each of us.